satellite orbiting Earth is actually in continuous free fall. Yes, it keeps falling towards Earth. But it moves sideways so fast that it keeps missing the Earth. For circular orbit, gravitational force provides centripetal force. Gmm by r squared equals m versus squared by r. This balance keeps the satellite in stable orbit. The satellite feels weightless because it's in free fall, just like astronauts in ISS. Orbital velocity is the velocity needed to maintain circular orbit. From the balance of forces, mvo squared by r equals gmm by r squared. Solving, Vo equals square root of gm by r, or square root of gr for near surface orbit. For Earth, orbital velocity near surface is about 7.9 km per second. Notice the beautiful relation. Escape velocity equals root 2 times orbital velocity. Ve equals root 2 times v. Full attention. We will cover universal law of gravitation, acceleration due to gravity, Kepler's laws, gravitational potential energy, escape velocity, and satellite motion. Let's begin our journey to understand how gravity works. First, let's understand Newton's universal law of gravitation, proposed in 1687. C. Newton observed an apple falling and wondered, if Earth pulls apple, does it also pull the moon? Yes. Every object in the universe attracts every other object. The formula is F equals G times m1 times m2 divided by r squared. Here, G is the universal gravitational constant, equal to 6.67 into 10 to power minus 11 Newton meter squared per kilogram squared. Remember 3 key points. Force is always attractive. It acts along the line joining centers. And it follows Newton's third law, equal and opposite forces. Now let's derive acceleration due to gravity, denoted by small g. Consider a mass m at Earth's surface. The gravitational force on it is g times m divided by r squared. But we also know this force equals m times g, the weight of the object. So, mg equals gmm divided by r squared. Cancelling m from both sides, we get the beautiful formula. G equals gm divided by r squared. For Earth, g equals 9.8 meters per second squared, which we approximate as 10 meters per second squared in calculations. This is why all objects fall with same acceleration, regardless of their mass. Galileo was right. Now, does g remain constant everywhere? No. Let's see how g varies with altitude. At height h above Earth's surface, the distance from center becomes r plus h. So g at height h equals gm divided by r plus h whole squared. We can rewrite this as g times 1 divided by 1 plus h by r whole squared. For small heights where h is much less than r, we use binomial approximation. G at height h approximately equals g into 1 minus 2h by r. Important point. As altitude increases, g decreases. That's why astronauts feel weightless in space stations. What happens when we go inside the Earth? This is variation of g with depth. Here comes an interesting concept. Only the inner sphere of Earth contributes to gravity at any point inside. The mass of inner sphere is m times r cubed by r cubed. Assuming uniform density, after simplification, we get g at depth d equals g into 1 minus d by r. Notice this is a linear relationship. At the center of Earth where d equals r, g becomes 0. Yes, at Earth's center, you would be weightless. Mind-blowing, isn't it? Now let's study Kepler's laws of planetary motion. Discovered even before Newton, Kepler's first law is the law of orbits. It states that every planet moves in an elliptical orbit with the Sun at one focus. Not circular, but elliptical. The Sun is not at the center, but at one of the two foci of the ellipse. This explains why planets are sometimes closer to Sun, called perihelion, and sometimes farther, called aphelion. Kepler's second law is the law of areas, also called law of equal areas. The line joining a planet to the Sun sweeps out equal areas in equal intervals of time. This means dA by dt is constant. Practically, when planet is closer to Sun, it moves faster. When farther, it moves slower. This law is actually a consequence of conservation of angular momentum. Kepler's third law is the law of periods. Most important for numerical problems. T squared is proportional to a cubed, where T is time period and A is semi-major axis. The exact formula is T squared equals 4 pi squared by gm times a cubed. For two planets orbiting same star, T1 squared by T2 squared equals A1 cubed by A2 cubed. This law helps us calculate orbital periods and compare different planets' orbits. Now let's understand gravitational potential energy. It is defined as the work done to bring a mass m from infinity to a distance r from Earth. Using integration, we get U equals negative gmm divided by r. Notice the negative sign. Potential energy in gravitational field is always negative. At infinity, P is 0, which is our reference point. As you come closer to Earth, P becomes more and more negative. This negative P indicates a bound system. Energy is needed to escape. Gravitational potential is potential energy per unit mass. V equals U divided by m, which gives us V equals negative gm by r. The gravitational field E is negative of the gradient of potential. E equals negative dV by dr. At Earth's surface, V equals negative gr. SI unit is joule per kilogram or meter squared per second squared. Potential is a scalar quantity, making calculations simpler. Now comes a very important concept, escape velocity. It is the minimum velocity needed for an object to escape Earth's gravitational field and reach infinity. Let's derive it using energy conservation. At surface, total energy equals kinetic plus potential energy. At infinity, both k and p become 0. So, half m versus E squared minus gmm by r equals 0. Solving, VE equals square root of 2 gm by r, which equals square root of 2 grams r. For Earth, escape velocity is 11.2 kilometers per second. That's why rockets need such high speeds to leave Earth. Let's now study satellite motion, very important for NEET. A satellite orbiting Earth is actually in continuous free fall. Yes, it keeps falling towards Earth. But it moves sideways so fast that it keeps missing the Earth. For circular orbit, gravitational force provides centripetal force. Gmm by r squared equals m versus squared by r. This balance keeps the satellite in stable orbit. The satellite feels weightless because it's in free fall, just like astronauts in ISS. Orbital velocity is the velocity needed to maintain circular orbit. From the balance of forces, mvo squared by r equals gmm by r squared. Solving, vo equals square root of gm by r, or square root of gr for near surface orbit. For Earth, orbital velocity near surface is about 7.9 km per second. Notice the beautiful relation. Escape velocity equals root 2 times orbital velocity. VE equals root 2 times VO. This is a frequently asked formula. Time period of satellite is time taken to complete one orbit. T equals circumference divided by orbital velocity. T equals 2 pi r divided by VO. After substitution, T equals 2 pi times square root of r cubed by gm. Squaring both sides, T squared equals 4 pi squared r cubed by gm. This is exactly Kepler's third law. Newton derived Kepler's law from his gravitational theory. For geostationary satellites, T equals 24 hours. Same as Earth's rotation. Finally, let's understand the energy of an orbiting satellite. Kinetic energy, Ke equals half mvo squared equals gmm by 2r. Potential energy, Pe equals negative gmm by r. Total energy, E equals Ke plus Pe equals negative gmm by 2r. Important relationships to remember. Ke equals negative E. Pe equals 2E. And magnitude of Pe equals 2 times Ke. Total energy is negative, showing the satellite is bound to Earth. If total energy becomes 0 or positive, satellite escapes. Now some very important NEET and JEE exam tips. First, memorize key formulas. G equals gm by r squared. Escape velocity equals root 2 grams r. Orbital velocity equals root gr. Second, remember sign convention. Potential energy in gravitational field is always negative for bound systems. Third, for energy relations, total E equals negative Ke equals Pe by 2. Fourth, for variation of G, with height use 1 minus 2h by r. With depth use 1 minus d by r. Fifth, escape velocity is root 2 times orbital velocity. This comes in many MCQs. Sixth, Kepler's third law T squared proportional to R cubed is used in almost every numerical. Pro tip. In NEET, most gravitation questions involve direct formula application. Practice numerical problems daily. Thank you so much for watching this complete lecture on gravitation. If you found this helpful, please like this video and subscribe to Magpie Hub for more NEET solutions. Turn on the notification bell so you never miss our new videos. Keep studying, keep practicing, and you will definitely crack NEET and JEE. All the best. See you.